Hello and welcome back. In section 3.5, we get to work with implicit differentiation. So the idea here is that sometimes we have an equation that's maybe not solved for y. We might have, say, y to the 7th is worth x, and we want to find the derivative of y with respect to the variable x. So in this case, we have, I should write that down, we're finding derivative of y with respect to variable x. In this case, it's not too challenging to solve for y, and we can differentiate using the usual method. So we just raise both sides to the 1/7 power. That's an odd index. 1/7 power is the same as the 7th root, so we don't need the plus or minus that we would have needed for an even root. So y is x to the 1/7, so then dy dx is worth 1/7 x to the negative 6/7 power, just by the power rule. You may also see it written as 1/7x to the 6/7, or with a radical. Another option, though, is implicit differentiation. The idea here is that if either we don't want to get the output variable by itself, or in some cases we won't have the ability to, what we can do is differentiate both sides, sort of temporarily pretending that they're both independent variables. Only when we differentiate the independent, or my apologies, when we differentiate the dependent, we also have to multiply by dy dx. So, for example, if I'm differentiating y to the 7th, I would say that's 7y to the 6th, but we also would have to multiply by dy dx. Differentiating x, I just get a 1. X is the independent variable. I don't need to attach that. So this gets attached because y is the dependent variable. Also, some people think of it as the output variable. So dy dx, we would just divide both sides by 7y to the 6th. And y, as we saw, is the same as x to the 1/7. But 1/7 to the 6th is indeed the 6/7 that we expect. So they are equivalent, even if they didn't look equivalent right away. So this next one, we're going to look at cap f of xy. So this time we're treating them both as two separate independent variables and treating cap f as our output, our dependent variable. Two separate inputs. So cap f of xy will start with x squared plus y squared is worth 36. Hopefully you recognize at least this much of it from your college algebra days. Think about what shape that is, where it's centered, etc. So we're going to find a couple things from this. We'll find dy dx. So the derivative of y, treating x as the independent variable, and the slope of the graph at x equals 1. So we're looking to differentiate with respect to x, so I'll do that to both sides. So if they're equal to each other in the original, their derivatives have to be equal to one another. So derivative of x squared is just a plain 2x. We don't have to write the first power down. If it helps you to write it down and get rid of it the next stage, that's fine. Derivative of 2y, or of y squared, is 2y, but again, we're differentiating with respect to x, not y, so we also have to multiply by dy dx. So anytime you're differentiating something that's different from the variable down here, you'll need one of these attached. Derivative of a constant in any variable is always going to be 0. So 2y dy dx is negative 2x. We'll divide both sides by 2y. So dy dx is opposite of x over y. Now, it should make sense that this slope is dependent on two things, both an x value and a y value. Before, remember, I asked you to think about what shape this was, where it was centered, etc. If you don't recognize it, this is just a circle with a radius of 6. And our center is on the origin. So what the slope is at 1 depends on if we are up here when x is 1 or down here when x is 1. There's two different possibilities. That's why it depends on both the x and the y. So finding the slope of the graph at x equals 1, I need to look at both of those, so I need to find both ordered pairs. So to find my points, I go back to the original. So 1 squared plus y squared is 36. So y squared is 35. So y is plus or minus root 35. So these 2 points, I have 1 and root 35. I have 1 and negative root 35. So to find their slope, it depends on which point I'm looking at. So slope for this first guy, dy dx, is opposite of x over y. Our other slope, dy over dx, opposite of x over y. Negative over negative, that'll kick us back over to positive. And that does kind of fit with the general very quick and dirty sketch that I made here. The point that was down here in Q4 had a tangent line that was had a positive slope on it. Q1 tangent line had a negative slope on it, and that does work out with what we see here. So the next one, we just sort of keep growing them a little bit in complexity here. We'll find the equation or equations of the tangent line or tangent lines at x equals 3, given x squared plus 5 times xy plus y squared is negative 41. So to find the equation of the tangent line, I need two things, a point and a slope. So slope dy over dx. So we will differentiate both sides of this. So d dx of x squared plus 5xy plus y squared is worth derivative with respect to x of negative 41. Alright, so one piece at a time. Derivative of x squared is just a plain 2x. Derivative in the middle here is a little more complicated. This is going to be a product rule. Okay, derivative of 5x is 5. Keep the second factor of y. Product rule, so plus. Now I keep the first factor 5x and differentiate y. Derivative of y is 1. And we have to multiply by dy over dx, since we're differentiating a y with respect to variable x. So that part is our product rule here. Those two terms. Derivative of y squared, 2y times, don't forget your dy over dx. Other side, derivative of a constant is 0. Alright, so what we're going to do then to find dy dx, we'll treat this as if it's an equation, and that dy over dx is just a variable, even though it's, we know, a derivative and a ratio of infinitesimally small values. We can treat it as if it were just a variable like an x or a y to solve for. So a little bit of cleanup. 2x plus 5y plus 5x dy dx plus 2y dy dx equals 0. We want to get this thing by itself, so I'll move those two to the other side. And I can go ahead and factor as well. So 5x plus 2y each had dy dx attached, and I'll move the 2x and the 5y. So then dy dx, derivative of y, treating x as our independent, negative 2x minus 5y all over 5x plus 2y. So that's our derivative of y with respect to x. This is our original equation. So now I can find my points, and once I find the points, I'll also find the slopes that go with them. So to find the pointer points, we plug x equals 3 into the original. So 3 squared plus 5 by 3y plus y squared is negative 41. So we have y squared plus 15y plus 9 plus 41 equals 0. So y squared plus 15 times y plus 50 is 0. And this one is factorable over the integers. So y plus 5 by y plus 10 is 0. So y is negative 5, or y is negative 10. So I have my two sets of ordered pairs from that. So the points that we have, remember, those came about from letting x equal 3. So we have 3, negative 5, and we have 3, negative 10 for our points. So the slope, recall from the previous page, dy over dx, was negative 2x minus 5y over 5x plus 2y. So we plug these in one at a time to find the two different slopes available to us, and that will let us then write two equations for two separate tangent lines. So the slope for 3, negative 5, dy over dx So negative 2 by 3 minus 5 by negative 5 all over 5 by 3 plus 2 by negative 5. So let's see, so we have negative 6 plus 25 all over 15 minus 10. So that would be 19/5. So that's our slope for the first point. Our slope for the other guy, for the 3, -10, dy over dx, negative 2 by x is still 3, minus 5 times y is now a -10. And then do the same thing downstairs. Just a little substitution. So 5 by 3 plus 2 by -10. So dy dx, negative 6 plus 50 over 15 minus 20. So we have 44 upstairs and negative 5 downstairs, so negative 44/5. So then our tangent lines, remember a tangent line, change in y is slope times change in x. So our first tangent line and this is for the 3, -5. Change in y, y minus -5. It's the slope, 19/5 for that point, times change in x. So y plus 5 is 19/5 of x, and then minus 57/5. And so I'll subtract 5, which is 25/5. So then y is 19/5 of x, and then minus 82/5. Our other tangent line for 3, -10, same idea, change in y, so y minus -10 is the new slope for that point, negative 44/5 times change in x. So y plus 10 is negative 44/5 of x. Negative by a negative will kick us back over to positive. So 132/5. We'll subtract 10, which is, that is 50/5. So our other tangent line, y is negative 44/5 of x, and then plus 82/5. So it is possible to get two tangent lines out of a single problem. It just depends on what the original equation looked like. So I'm going to let you all try one out. So same idea, you're looking for the equation of tangent lines. This is one of your authors' examples. So x squared plus y squared minus xy minus 7 is 0. So find the equation or equations of the tangent line or tangent lines, and we'll do x equals 1. So go ahead and pause it, see if you can give this one a spin, and unpause it when you're done. Okay, tangent line, welcome back. Tangent line means we will need a derivative, so we'll differentiate both sides of this with respect to variable x. So derivative of x squared is 2x. Derivative of y squared is 2y times dy dx. And then again we have another product rule here. So derivative of negative 1x is negative 1, and keep the second factor y, plus, then we keep the first factor, negative 1x, and differentiate y, which is 1 times dy dx. Derivative of constant is 0. Derivative of this constant also 0. So this much of it was that product rule. Okay, a little cleanup. So we have 2x plus 2y dy dx minus y minus x dy dx equals 0. So the y moves over, the 2x moves over. We can factor the dy dx from the two terms left, leaving us a 2y and a minus x. So dy dx is y minus 2x over 2y minus x. You might have written it in a different order, as long as you have the right signs and coefficients. Addition is a commutative operation. Okay, so we're talking about what's happening at x equals 1. So for our point or points, we let x equal 1 in the original. So 1 squared plus y squared minus 1y minus 7 is 0. So we'll clean up y squared minus y, and we have 1 squared is 1, 1 minus 7 is negative 6, equaling 0. So y minus 3 by y plus 2 equals 0. So y is 3 or y is negative 2. So we have two possible ordered pairs from that. One was the x for both of them. So let me make a little bit of room here. We'll just flip to the next side. So the points we have to work with, we have 1, 3, and we have 1, negative 2. So our slope, recall that dy over dx was y minus 2x over 2y minus x. So dy over dx for the 1, 3, y is 3 minus 2 times x is 1 over 2 times y is 3 minus x is 1. So dy over dx, our slope at 1, 3, we have 3 minus 2 upstairs and 6 minus 1 downstairs, so we have 1/5. Our slope for the other ordered pair, dy over dx, y is negative 2, minus 2 times x is 1. 2 times negative 2 minus a 1. So dy dx for the ordered pair 1, negative 2, we would have upstairs negative 2 minus 2, downstairs negative 4 minus 1. So that would be a negative 4 over negative 5, which is a positive 4/5. So tangent line at 1, 3, change in y is the slope times change in x. So y is 1/5 of x minus 1/5 plus 3 is 15/5. So y is 1/5 of x plus 14/5. For a tangent line at 1, negative 2, same idea, change in y is the slope times change in x. So y plus 2 is 4/5 of x minus 4/5. So I'll subtract 2, which is 10/5. So then y is 4/5 of x minus 14/5. So there's our other tangent line. One other sort of common application with the implicit differentiation involves different variables than the ones we're used to using of just an x and y. Sometimes we're looking at variables of time and some other unknown x. When that's the format, time is treated the way x used to be treated, x is treated the way y used to be treated. So time t gets treated like the x, and the x gets treated how we used to treat the y. So for example, they may ask us to find x prime of t for t squared natural log of x is worth x e to the t minus 1. So we're going to differentiate both of these with respect to, this time, t, not x. Watch out for that guy. So differentiating with respect to independent variable t. So left-hand side, this is another product rule. So the derivative of t squared is 2t. And I would hang on to natural log x. Hang on to my plus sign because it's a product rule. And then they trade roles. I'll hang on to the t squared, and I'll differentiate natural log of x, which, if you'll recall, is 1 over x. But again, since we're doing that with a different variable, this and this don't match, we also have to attach a dx dt. So that's our product rule on the left side. On the right side, we have another product rule coming up. So derivative of x usually is just 1, but again, we're differentiating with respect to t. So it would be 1 times dx dt. Keep the second factor e to the t, plus sign because we're working with a product rule still. Then we'll keep the x and differentiate e to the t, which is e to the t. These variables match. I don't have to attach a differential. Derivative of a constant drops it off entirely. So just a little cleanup to make it prettier, and then we'll solve for dx dt, which will then give us x prime of t. So let's see, we've got 2t natural log of x plus t squared over x dx dt is worth e to the t dx dt. So just the commutative property of multiplication there, plus x e to the t. So then I want the dx dt's on one side, all the other stuff on the other side. So I'll have a t squared over x and a minus e to the t. Each of those is multiplied by dx dt. On the other side, I had an x e to the t already, and I would subtract this 2t natural log of x. So on this one, just a little bit of cleanup to go to make things a little easier. I'm going to go ahead and put a 1 under here, and to get a common denominator, we're going to hit it top and bottom with an x. We'll multiply by something worth 1. So then I have t squared minus x e to the t over x times dx over dt is worth x e to the t minus 2t natural log of x. So that way I have just one nice, neat, pretty fraction. If I want to divide by a fraction, I can just multiply by the reciprocal. I can just flip it. So flipping it, then we have dx dt by itself. And we had an x e to the t minus 2t natural log of x. And that whole thing gets multiplied by an x up top and a t squared minus x e to the t downstairs. And let's see, I don't see much in the way of useful factoring here. So we'll just do a little cleanup there. So then they asked us to call it x prime of t, so we can translate it now. Dx dt is the same as x prime of t. So that would be x squared e to the t, so I'm distributing the x, minus 2 tx natural log of x, and then downstairs t squared minus x e to the t. And that's as much as we can clean that up on. Alright, so let me have you all try one out. So we're going to find x prime of t. Let's see, we'll do 1 plus x natural log of t is worth t e to the x. And I'll also ask you to evaluate, this is another one of your authors, at 1, 0. So go ahead and pause it and come on back when you're done. Welcome back. So find a derivative. We will differentiate both sides with respect to our independent variable t here. Derivative of a constant is 0. That term just drops off, and we have another product rule here. Derivative of x is 1 times dx dt. Keep your second factor, or in this case, natural log of t. And then plus, now they trade roles. Now I hang on to the x and differentiate natural log of t. 1 over t. On the other side, product rule again. Derivative of t is 1. Hang on to your second factor, e to the x. Then they trade roles. Now I'm going to hang on to t. Derivative of e to the x is e to the x times dx dt. So not too much cleanup to do there. So we have natural log of t times dx dt plus x over t. It's worth e to the x plus t to the x dx dt. Get all your dx dt's on one side, everything else on the other side. So we'll have natural log of t minus t e to the x. Each had a dx dt. And we had e to the x, and I would move the x over t to the other side. And again, same idea. I'm going to get a common denominator here. Multiply top and bottom, in this case, by t. So then we have dx dt on the left-hand side. And on our right-hand side, we would have t e to the x minus x, which was over now common denominator t, and that would be multiplied by the reciprocal of our coefficient of the dx dt, so natural log t minus t to the x. So not much cleanup to do, just a little distributing here. And then dx dt, t e to the x minus x over t natural log t minus t e to the x. So part one of just finding that is our x prime of t. Part two, they were asking us to find what's happening at 1, 0. So remember that is in the order t comma x. So dx dt, so the slope of the tangent line at this point 1, 0, so 1 for every t, 0 for every x. So dx dt at 1, 0, 1 e to the 0 is 1. So 1 minus 0, natural log of 1 is 0. And e to the 0 is 1. So we have 1 over negative 1, which is negative 1. So that would be the slope of our tangent line at 1, 0. All right, so some problems to try out. This was section, here we are. So this was 3.5. Try out 1 to 41 on the odds, and 45 to 51 also on the odds. So if you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.